All right, next we will look at acceleration, which is defined as the rate of change of velocity or speed. It has units of distance per time and like meters per second squared or kilometers per hour squared or miles per hour per second. Let's explain that. Before we get into that, let's say as well that an object moving at constant velocity is said to have zero acceleration. If the velocity is constant, then it's not changing, and the rate of change of velocity or speed is going to be zero. Let's look at the units of acceleration. Imagine you were traveling at 35 kilometers per hour. Per 1 hour, and then you sped up to 50 kilometers per hour per 1 hour. You would have a change, or a delta v, of 15 kilometers per hour. And let's say that it took 5 minutes to do that. Let's say 5 seconds, actually. Let's say 5 seconds. It took 5 seconds to do that. Every second that went by, your speed would have changed by a fifth of this total, assuming that you're accelerating at a constant rate. And so our rate of acceleration would be a fifth of this, 3 kilometers per hour every second. Now, let's acknowledge that speed can be measured in kilometers per hour as well. It can be measured in meters per second. And so if we had been talking in meters per second the whole time, our acceleration would be equal to 3 meters per second, a change of 3 meters per second every second. And so if we had been talking about meters per second, in terms of meters per seconds the whole time, then our acceleration would take a value of 3 meters per second, or 3 meters per second squared. And in this case, in this course, we'll be considering problems only with constant acceleration because we can solve those using algebraic methods. And in terms of equations, we can mathematically calculate acceleration, be it a vector or a scalar, using these. Acceleration equals your final speed or velocity minus your initial velocity divided by your final time minus your initial time. Usually, you'll be given an elapsed time. And so acceleration equals your final speed minus your initial speed divided by time. These could also be velocities, in which case your acceleration would be a vector. This can also be written as acceleration equals delta v divided by delta t. We can also rearrange that second equation to say that v2, or your final speed, equals your initial speed plus a delta t. Remember that a delta t equals a change in velocity. We took a look at that just now. So this is your change in velocity. Here's your final speed. Here's your final speed, here's your initial speed, and here's your change in speed. So your final speed is just how fast you were going plus how much your speed changed. And so this equation relates your velocity at any given instant in terms of your starting velocity, and here is the change in velocity you could also be talking about speeds if those were the values you were given. This is another equation that may be useful, that will be useful certainly. Your distance is equal to your initial speed times the time you traveled, plus 1/2 of your acceleration times time squared. This is also valid in vector form with displacement equaling your initial velocity plus 1/2 of the acceleration times time squared. This first term that you see in this equation tells us how far you would have traveled had you just been going at a constant speed the whole time. The second term over here gives us an additional displacement associated with the fact that we had sped up. We didn't travel at this initial velocity the whole time. And so if we were to check units, this first portion, velocity comes in units of meters per second times units of seconds. These will cancel. This will come in units of meters then. Acceleration over here comes in units meters per second squared times time squared. We'll have units of seconds squared. These will cancel. The second term will also have units of meters, and our displacement or distance will have units then of meters plus meters or meters, which is appropriate if, again, if your units don't agree with the quantity that you're solving for, then something's wrong and you need to go back and check your work. And so let's do an example. A body with an initial velocity of 8 meters per second east is accelerated at a rate of 1 meter per second squared east. What is its displacement after 30 seconds? Well, let's first identify all of the information given. We have a velocity of 8 meters per second east. We have an acceleration of 1 meter per second squared east. We have a time, an elapsed time of 30 seconds. So we'll use v1 for initial velocity, 8 meters per second east. We have an acceleration of 1 meter per second squared east, and we have a delta t of 30 seconds. We're looking for a displacement. Now let's take a look at the equations we've dealt with so far. We have average velocity equaling displacement divided by time. We have average speed equaling distance traveled divided by time. We have acceleration equaling delta v over delta t. We have this one. And we have this. Think of these equations as your tool chest. And not every tool is appropriate for every job. And so the job we want to accomplish is finding delta d, and so our displacement. And so if we're to do that, then we need to find an equation that contains delta d, like this one doesn't, and this one doesn't, and this one. Now, Here, we do have a time. We can find delta d. It's in there. We can isolate that. We don't have an average speed, or average velocity. And so as written, we won't be able to use this. However, this one, so this, not useful in this case. We have a v1, we have a figure for delta t, we have a figure for acceleration, and again for delta t. We can use this equation then to find our displacement after 30 seconds. And so we don't even have to rearrange anything to do that. We can say that delta d equals v1 delta t plus 1/2 a delta t squared. And that will equal 8 meters per second in the east times 30 seconds plus 1/2 times our acceleration times our time, which is going to be squared. This first part works out to 240 meters east. 30 squared is 900, times 1 is still 900, times 1/2 is going to be 450 meters east, for a total of 690 meters in the east as our displacement. To practice, I suggest you do the following questions in the Shams textbook, 11th edition, page 11, questions 119, 120, 121, 123, 125, and 126. Also on page 26, there are a few questions that also apply.